Okay, so hello everyone and welcome to this lecture. Today we're going to be talking about two different topics. Each topic will take around half a lecture. So the first topic is cache coherence. This is an issue we deal when we use caches in a context where you have multiple cores accessing the same data. And then the other topic is cache-aware optimizations. Okay, and this is going to look at specific optimizations that we can apply to code that take into consideration how the code is interacting with the cache. Okay. Okay, so we'll start with talking about cache coherence. So what is the cache coherence problem? Consider a scenario where we have two different cores inside of a processor. Okay. Typically, when you have multiple cores, the first level of cache, right, is private to each core. So each core has its own cache. Okay, so you have two different cores, each core has its own cache. And of course, the memory is shared by all the cores, right? You have one big main memory, DRAM, inside of your CPU that is shared or inside your system, that's shared by all the different cores. And now let's assume we have a scenario where we have some memory location X that has value 3. Okay, and this value is in memory. And let's assume that core A reads X, right? So if core A reads X, what's going to happen? Right, we're going to bring in X to the cache of core A. So X is going to come into the cache of core A. Okay, now let's assume that core B reads X. What's going to happen with X now? Right, same thing, right? So core X is going to come to core B, and it has to go into the cache of core B on its way. Okay, so now each of core A and core B each have X inside of their cache. Okay, now let's assume that core A writes to X. Okay, let's assume core A writes to X. Maybe it writes the value 5. Okay, now if this is a write back cache, okay, what's going to happen is this value here will change to 5. Okay, this value will stay 3. Okay, if it's a write through cache, this value will change to 5, right? And then this value becomes 5. Okay, but what happens to this value? The value that's in core B's cache, right? Somebody's saying it remains 3. Should it remain 3? Is it correct for it to remain 3? It shouldn't remain 3, right? So when core A writes to a value that's in somebody else's cache, right? We can't have core B keep the value 3 because when core B reads this value, it shouldn't see 3. It should see 5. Okay, and if this happens, which hopefully it doesn't, right? If this happens, we say that the caches are incoherent. We don't like caches to be incoherent because it messes things up, right? It makes the data it's not what the programmers expect when they access data in multiple cores. We would like caches to be coherent, so we need a way to maintain coherence between these two caches, such that when core A modifies a value and core B subsequently accesses that value, it doesn't see the wrong value. Okay, so we refer to this as the cache coherence problem. Actually, we just talked about cache coherence problem. A mechanism for us to maintain this coherence between caches is a cache coherence protocol. Okay, so a cache coherence protocol is a sequence of operations that caches perform to ensure, when you have multiple processors, to ensure that the caches are coherent. Okay, it's something that the caches do in order for them to make sure that whenever there's a value in multiple caches, that value is coherent across all the caches and different processors are not accessing incoherent data. There are two major categories of coherence protocols. One major category is snooping protocols. And in a snooping protocol, what happens is there's a shared bus across all the caches. And each core monitors that bus, finds out what the other cores are doing by looking at what's going on that bus, right? And responds in a way to make sure that the data is coherent. Okay? That's what a snooping protocol is. There's also directory-based protocols, and directory-based protocols are basically where you have some kind of centralized directory that's responsible for maintaining coherence, and all the processors, they communicate with that centralized directory when they do their memory accesses to make sure that the caches are coherent. Is this clear? Any questions? Okay. So we're not going to go into too much depth into cache coherence protocols, right? There's an advanced course on computer architecture where you can look into that in a lot of depth. But today what we're going to do is we're just going to look at, just to give you an example of the things that happen when you have to deal with cache coherence. We're going to look at a very simple snooping protocol for cache coherence, and that's the MSI snooping protocol. Okay, so we're going to look at a simple snooping protocol called MSI. Okay, MSI stands for the three different states, M, S, and I, that a cache line can be in, or cache block can be in, with respect to this protocol. Okay, so under the MSI protocol, each block can be in one of three different states. There's the modified state, the shared state, and the invalid state. Okay, the invalid state, that's where the MSI comes from. The invalid state represents when a block is not in the cache. Okay, and we've seen this before, right? You have these valid bits, and then you can have valid, invalid, right? So invalid state represents when a block is not in the cache. A shared state represents when a block is in the cache, okay, but it hasn't been modified. Now, if a block is in the cache, but it hasn't been modified, that means it's okay for this block to be in multiple caches, right? Because as long as you don't modify a value, if you're just reading it, it's okay for multiple processors to have the same block and to be reading it. And then finally, you have the third state, which is the modified state. And the modified state is where a block is in the cache, and also we've modified that block, okay? That's like the example where you had core A wrote 5 to X, right? It modified it. Now, when a block is in the modified state, which means that a certain core has modified a certain cache block, obviously that block should not be in other parts of in other caches of other blocks, because then it will be incoherent. Okay, so these are the three states. We can also define transitions between these states. Okay, so a block is going to be in different states at different times. It's going to transition from one state to another based on certain events. Okay, what are the events that could happen? Right, I'm making some simplifying assumptions here, but what are the events that could happen that affect the coherence or the state of a block? I could have a local read, which means the core that owns this cache reads a certain block. I could have a local write, which means the core that owns the cache writes to the block. I could have a bus read. A bus read means that I received some message on the bus that tells me that some other core read a block. Okay, which means somebody else reads, some other core, not the core that I'm focused on. And then a bus write is where some other core writes to the cache, or writes to the block. Okay, so either I read a block, or I write to a block, or somebody else reads the block, or somebody else writes to a block. These are the four events that impact how we transition between the different states. Is this clear? Any questions? Okay, so we have states, we have transitions. What can we do to be able to kind of visualize what happens and how we transition between states? You guys remember state diagrams? We covered those earlier in the course. So let's design a state diagram for the MSI protocol. Okay, remember we had three states. What were they? Right, invalid, shared, and modified. So these are going to be our three states. Okay, next, what we're going to have to figure out is, for each one of the events that could happen, local read, local write, bus read, bus write, how do we transition between states? Okay, let's start with the invalid state. Okay, if I'm in the invalid state and I have a local read, which means a certain block is invalid in my cache, and then I read to that block. What state does that block transition to? If I read a block, right, I go to the shared state, right? I go to the shared state because it was invalid. I didn't have it. I read it, right? So I'm going to bring it into my cache, but I'm in the shared state because it's okay if other people also read it, right? No problem if somebody else has it, somebody else is reading it, because I'm only reading it, I'm okay with sharing it. So we go to the shared state. What if I'm in the invalid state and I want to write to a block? Right, if I'm in invalid state, I want to write to a block, I go to the modified state. This means I brought the block in and I also modified it. Okay? What if I'm in the invalid state and somebody else reads the block? Does that affect me? No, right? It doesn't affect me because, I'm invalid. If somebody else is reading, I don't care, right? I'm not gonna change the status of the block in my cache, right? So bus read is going to keep me in the invalid state. What about bus write? Somebody else writes to the block? Same thing, right? I'm invalid. There's no point in modifying my state. Okay, so bus write keeps us in the invalid state. Clear? Questions? Okay, now let's focus on the shared state. The shared state means that I have the block in my cache, but I haven't modified it, right? It's only been read, and it may or may not be in other people's caches, right? Other people might also be reading it. That's completely fine. It's legal. Okay? So if I'm in the shared state, I have the block, I'm reading it, so other people might be reading it. And let's say I read the block again, right? I do a local read, right? I have shared state, I have a local read. What happens? I'm going to stay in the shared state, exactly. So we're going to go back to the shared state. So we'll get to bus reads. Somebody's asking about bus reads. We'll get to bus reads. Okay, what if I am in the shared state and all of a sudden I decide I want to write to the block? Right, exactly. If I want to write to the block, I need to move to the modified state. Okay? I need to move to the modified state. I need to indicate that now I'm modifying this block, so other people have to be careful. Okay? What if I'm in the shared state and somebody else reads the block? So same thing as local read, right? If we get a bus read, we're gonna stay in the shared state, right? If I'm reading the block, other people are reading the block, that's fine. We're sharing, so there's no problem. What if I'm in the shared state, so I'm reading the block, and then somebody else decides they want to write to the block? Okay, so somebody's saying we either go to modified or we go to invalid. Let's say which one. Can we stay in the shared state? Right? If somebody else writes to a block, right, that means we're going to have the wrong value. Okay, somebody else is writing to the block, we're going to have the wrong value. Okay, so we cannot keep that value in our cache. Okay. We're not in the modified state now, we're in the shared state. So let's focus on the shared state. Okay, we can't go modified. Modified means that I modified it. Okay, but but somebody else modified it in this case. If somebody else modifies a value, okay, my value is no longer the most up-to-date value. Okay, so that means that next time I read it, I shouldn't read the value that I have. I should go and get the most up-to-date value from wherever it is. So what happens is, in the MSI protocol, is if I have a value in my cache and somebody else writes to that value, I'm supposed to invalidate my value, so to make sure that the next time I read it, I go get the most up-to-date value. Okay, so now if we go back, if I'm in the shared state and I get a bus write, somebody else writes to the value, what should I do? I should go to the invalid state, exactly. So bus write takes me to the invalid state. Any questions? All clear? Okay. Now let's go to the modified state. Let's say I'm in the modified state. Okay. And then I decide to read the value that I have. Right, I stay in the modified state. Remember, when I'm in the modified state, it means I'm the only one that has this value, nobody else has it, right? Because when I modified it, everybody else invalidated their values, okay? So if I'm in the modified state, I read, I stay in the modified state. What about if I'm in the modified state and I have a local write? I decide to write to the value. I can stay in the modified state, no problem, right? So local write keeps me in the modified state. What if I'm in the modified state and then somebody else wants to read the value? So if I have a bus read. So somebody's saying the other block is invalid. That's right. The other block is invalid. We're not focusing about the other cache. We're not focusing about the other cache state. We're focusing on our state, right? If I'm the core that owns this value, I've modified it, but then now somebody else wants to read it. That's right. I should go back to shared, right? Because if somebody else reads it, right, this means that in the future, if I want to write to it again, I need to make sure that to change, if I want to read it in the future, that's okay. But if I want to write to it in the future, I need to tell everybody else again. Okay. So if I'm in the modified state and somebody else reads the value, I need to keep track of the fact that, okay, now this value is present in other people's caches. So we're going to move to the shared state. So bus read takes us to the shared state. And if I'm in the modified state and somebody else writes to the value, what should we do? We go to the invalid state, right? If I'm in the modified state, somebody else writes, that means that somebody else who just wrote is going to move to the modified state. We are going to have to invalidate the block to allow other people to write to it. So we're going to go back from the modified state to the invalid state. Okay, so this is a state diagram, okay, that represents how the MSI protocol works. There are more sophisticated protocols that are more optimized, right? There is a MESI protocol that has MESI that has an additional exclusive state. There are also more sophisticated protocols, and we've taken state diagrams and we've taken state machines, so you can probably imagine how we can implement such a protocol inside of our system. That's not the focus of this course, so we won't go into more details on cache coherence. But the idea here is just to kind of make you aware of the kinds of things that we need to consider when designing caches in a multi-core system. Okay. Any questions about cache coherence? All clear? Yeah? Okay. Okay, the next topic we're going to look at, kind of an independent topic, is writing code in a way that takes into consideration caches when optimizing that code for performance. Let's consider the case where we have a 2D array. And we want to go through that 2D array and we want to add all the elements in that array. Okay? The code for that is going to look something like this, right? I initialize some variable sum to 0. Okay? And then I loop over the columns, loop over the rows. Okay? And then I accumulate into sum the value at that row or column. Okay? So this would look like this if I have this 2D array, right? I'm going to do for every row. And then for each row, I'm going to do for every column. And then for each column, I'm going to do for every row. I'm going to go down, right, and access each value and add it to the sum, right? And I will go through my array like this, okay? So this is what this code does. Clear? Okay. Now, let's think about how this code interacts with the cache, okay? When we store arrays in C, when we represent 2D arrays in C or C++, the way that these 2D arrays are represented is in something called row major order. Okay, row major order means that you're going to have all the elements in the first row next to each other, followed by all the elements in the second row, followed by all the elements in the third row, followed by all the elements in the fourth row, etc. Okay, so in this 2D array that we're adding right here, okay, the way that these matrix elements or array elements are placed in memory is you're going to have the first value in the first row, then the next value in the first row, then the next value, then the next value, then the next value, etc. And when you're done with the first row, you're going to go back. You're going to have the next value, the first value in the second row, then the next, then the next, then the next, etc. This is how the elements are laid out in memory. Okay. Now, if we think of caches and cache blocks, right? A cache block is typically multiple words. Let's say that we have, just for example's sake, let's say that we have a cache block that fits 4 words. Okay. In this case, the first 4 words in our matrix, right, or the first 4 elements are going to be in the same cache block, right? The next 4 words are going to be in the same cache block, etc. Now, if we look at the way that we're accessing this matrix, okay, we start with the first element, but what we're doing is we're going downwards, okay? So after we access the first element in the matrix, right, what's going to happen is these other 3 elements are also going to come into the cache, right, because they're all part of the same cache block. However, what we're doing is we're going down, okay? So when we go down, we're going to get another cache block and use the first element in that block. When we go down, we're going to get another cache block and just use the first element. And then we keep going down and getting a whole cache block and using one element in that cache block, right? If this is a very big array, right, over here in my example, I have an array that's 4K by 4K, right? If this is a very big array, by the time I've come all the way down here, it's likely the case that this first cache block that has these first four elements has been evicted from the cache. Correct? So when I come back and I want to access this element, the top element in the second row, okay, it's most likely the case that this element is no longer in my cache. I'm going to have a capacity miss. Clear? Okay. So what can we do to avoid this? What can we do so that when we bring in we don't miss on every single element. When we bring an element into the cache, we make sure that we use all the blocks in our cache before we, all the elements in the block before we lose them. Yes.
Getting one element, get the whole bird,
Right, exactly. So all of you are kind of alluding to the same idea. So what we can do is, instead of accessing the matrix vertically like this, what we can do is we can load the first element and then go horizontally, use up all the elements, right? Then load the next cache block, use up all the elements, etc. So that would look like this, right? So if we interchange these two loops, before we did for every column, then for every row. If we interchange the loops, we do for every row, for every column. Now we're looping over the rows first, and then inside of each row, we're looping over the columns. So now what this code will do is it'll access the first element, then the next, then the next, then the next, uses up the entire cache block, and then moves on and starts accessing the next cache block. Okay? So now we're utilizing the cache blocks better. Now we're going to have fewer cache misses. We're going to have fewer capacity misses. We're going to have more hits. The hits are taking advantage of what in this case? Spatial locality, exactly. This program has better spatial locality than the previous program that we wrote. Okay, so interchanging the loops improves spatial locality. Is this clear? Okay, is this clear? Any questions? Okay, let's actually do an example of this, right? So I prepared some code that we can look at. Okay. Okay, so I prepared here some code that does basically what we've been looking at. So here you have this function sum2d that sums the tech gets the sum of a 2D array. It takes an array that's 4096 by 4096, initializes the sum to zero, loops over every column. For every column, loops over every row, and accumulates. Okay. Let's compile this code, run it, and see how it performs. And then we'll interchange the loops and compile it and run it again and see how it performs. Okay? So I'm going to compile it. In another course, we'll do that. Okay, so we compile it. So here G++ is my compiler. I give it the file that I want to compile, and I tell it to give me the output binary as mul. Okay, and now we can run it. Okay, and here it takes 230 milliseconds to run. Okay, and gives us what the final output is. Clear? Yeah? Okay, now what we want to do is we want to interchange the loops and see how that impacts the performance. Okay, so we're going to open the code again. Okay, and this time I'm going to interchange the loops. I'm going to delete this. Oops. Right, and now we're doing for every row, and then we do for every column. Okay, so for every row, we iterate over the rows. Okay, and then we do for every column, iterate over the columns. Okay, so what do you expect? How do you expect the performance to change? No, this will be faster, right? This will be faster, okay? Because it will, we expect it to be faster because it will have better spatial locality. So we're going to compile again. We can tell it to give us mul as our output. Okay, and now we're going to run mul. And you'll see that our time went from 230 milliseconds to 39 milliseconds. Okay, so that's almost a 6 times, right, performance improvement because we are interacting with the cache in a more friendly way because our program is written in a way that has better spatial locality. Okay, is this clear? Any questions? All clear? Okay. Okay, great. So now we've seen how this improving spatial locality helps with improving the performance of this code. Let's go to an even kind of more important computation, which is matrix multiplication. Matrix multiplication is very important. Okay, you're going to see in future courses that it's used everywhere. Okay, all kinds of scientific simulation code, machine learning, all kinds of applications can be formulated and implemented as matrix multiplication. Okay, so how does matrix multiplication work? I believe most of you have taken a linear algebra course, so you're familiar with matrix multiplication. So matrix multiplication looks like this. Okay, you have three nested loops for every, and you have two matrices, A and matrix B. These are my two inputs, and you have an output matrix C. Okay, and the way matrix multiplication works is that every output element in matrix C is going to be the dot product of the corresponding row in matrix A and the corresponding column in matrix B. Okay, clear? And the way it's implemented is like this. You have for every row, for every column, so these first two loops iterate over the output, the matrix in the output, the elements in the output matrix, right? So you do for every row of C, for every column of C, right? So now these first two loops are iterating over the output elements. And then for each output element, what you do is you iterate through the row and column of the input matrix. So you do for every, here we're labeling that as I, so I iterates through the row and the column, okay? And what you do is you do a multiply and add, right? You're doing a dot product. So you take the element at row I of matrix A, the element at I column of matrix B, you multiply those and you add them to the value that you're accumulating for at row column in matrix C. Okay, so this is how matrix multiplication works. Now, following what we saw in matrix and when you're taking the sum of a 2D array, right? If we assume that A and B are both in row major order, they're stored in memory in row major order, where do we have a source of inefficiency in the way that we're accessing these matrices?
The second order.
Right, exactly. We have an inefficiency in the way that we're accessing matrix B. Okay? In particular, what's happening is, you know, we have, when we load this first element in B, right, these other elements are coming in with it into the cache. Okay? But when we go all the way down to the end, to the bottom of the matrix, and then come back up for the next element, what's going to happen is these elements that we loaded are no longer in our cache. Okay? If the matrix is very big, this might also happen for matrix A, right? We are going to access all the elements in the cache block, right? But when we go to access to compute the next element of C, we're going to go through the same row again, right? But if the row is very large, right, we might have the initial cache block in the row is already evicted by the time we need to access it again. Okay? So what can we do to improve performance? Ideally, what we'd like to do is we'd like to bring in a block into the cache, use it as much as possible before it gets evicted. Okay? So instead of accessing kind of a lot of places in memory at the same time, we'd like to change our program to where we access small parts of the memory and we access them a lot, as much as we can, and then we move on to access other parts of the memory. Okay, and this is referred to as tiling. Okay, what we do is we're going to divide our matrices into tiles. Okay, so here our output matrix, we're going to divide that into tiles. Our input matrices, we're going to divide them into tiles. Okay, we're going to choose the sizes of these tiles in a way that the tiles fit into the cache. And then what we'll do is when we want to compute this output tile, okay, we're going to start by taking one tile of the input, one tile of the other input, and multiplying those together to calculate the partial sums or partial values of the tile of the output. And once we're done computing all the contributions of these elements and these input elements to these output elements, we move on and we go and get elements in the next tile. So we go to the next tile, we're going to compute the contributions of these elements and these elements to this output element, right? And when we're done reusing the data as much as possible, we move on to the next tile and we do the contributions of these elements and these elements to these elements, okay? So if we focus on a single element and what's happening to a single element, let's focus on this, the first output element in the tile of C, right? What's going to happen is initially what we're going to do is we're going to take this row of the tile of A and this column of the tile of B, okay? And we're going to calculate their accumulation to this first element, okay? Now, because the tile is not big and this tile is not big, both of these tiles will fit inside of our cache, right? So all the blocks in these tiles will fit inside of the cache. So when we're done doing the partial accumulation for the first element and we go to the next element in the output tile of C, we're going to go and find that, oh, these other elements haven't been evicted yet, okay? Because the tile is small enough, all these cache blocks fit in memory, okay? And same thing here, we're going to come back and we find, oh, this row hasn't been evicted yet, because these tiles are small enough that they all fit, not fit in memory, fit in the cache at the same time, okay? So we pick the sizes of these tiles to where this whole tile and this whole tile and this whole tile fit all in our L1 cache at the same time. Is this clear? Any questions? Okay, so the code for doing this, right? So we said we're going to do these tiles and we're going to do one tile at a time. So the code for doing this is going to look like this. It's going to be 6 nested loops. We iterate over the output tiles, right? We iterate through the input tiles. We iterate through the output elements in the output tile, and we iterate through the input elements in the input tiles, right? So if we go back here, what we do is we do for every row of input tiles, okay? For every tile in the row of input tiles, now this brings us to every row of output tiles. For every tile in the row of output tiles, this brings us to one output tile. These are the first two loops. The third loop is going to iterate through the input tile. So it does, okay, for this first input tile, for this second input tile, for this third input tile. Okay, so now we have 3 loops. The fourth and fifth loop are going to go through the output elements in the output tile. So we do for every row of output elements, and then we do for every column or for every element in each row of output elements. And then the sixth loop will do for every input element that corresponds to that output element. So the sixth loop will go through this strip of input elements and then this strip of output elements, okay? And that's what these 6 nested loops do. Again, the first 2 loops go through the output tiles. The third loop goes through the input tiles that accumulate to that output tile. The fourth and fifth loop iterate through the elements in the output tile. And the sixth loop iterates through the input elements from the input tiles that accumulate to that output element in the output tile. Okay, so the code is a little bit more complicated. Okay, but let's go and see how it affects performance. Okay, let's go and see how it affects performance. Okay, I'm going to switch back to the terminal right here. Okay, so I have two implementations of matrix multiplication. This is the first implementation that we looked at. Okay, as you can see, we do for every row, for every column, and then we do a dot product of the corresponding row and column in A and B, right? So these first 2 loops iterate through the output elements in the output matrix, and the third loop goes through the input elements corresponding to that output element and does the dot product. Okay, let's compile this code, execute it, and see how it performs. Okay, so I'm going to do compile. I'm going to turn on a command because this is so big. I'm going to turn on a command. -03 tells the compiler to apply a lot of optimizations to this code so that it runs efficiently, right? And then I'm going to just call this, let's just call it mul. Okay, I think I was calling the previous one mul. I shouldn't have done that, right? I should have called it add or something. Okay, but I was thinking of this example while doing that other example. Okay, so what we did is we compiled, we applied optimizations, and now we have our mol.exe, so we can run this. Okay, and we'll wait for it a little bit. Right, we're doing 2k by 2k matrices, right? So this, matrix multiplication is O of n cubed, right? So we're doing 2k cubed operations, right? So that's a lot of operations. So might take a while. Yeah, Vim is a text editor. It's taking quite a while. This is so that you can appreciate the importance of performance optimizations, right? If it took 5 milliseconds and the next version took 2 milliseconds, you'd be like, oh, this is not that important. So now this helps you appreciate how important it is. Okay, so we have, how long did it take? So it took around 58 seconds, right? It took around 58 seconds to do a 2K by 2K matrix multiplication. Okay, now let's go look at the tiled version and see how the tiled version performs. Okay. Okay, so we look at the code for the tiled version. Oops, let me zoom out a little bit. It's not zooming out for some reason. Well, it's not zooming out for some reason, but I mean, this is the code that I showed you in the slides, right? You have 6 nested loops, loop that iterates, the first 2 iterate over the output tiles, the third loop iterates over the input tiles, and then for each set of tiles, you have the first 2 loops iterate through the output elements in the output tile, and then the last one iterates through the input elements in the input tiles. Okay, I'm going to compile this. Okay, and now I'm going to run it. So remember, the other version took around 58 seconds to run. So this one took how much? It took around 9 seconds, okay? Around 9 seconds. So we went from 58 seconds down to around 9 seconds. That's a major performance improvement, right? From just doing something as simple as tiling. And there are more complex optimizations that we can apply to matrix multiplication to make it go faster. The compiler might already be applying some of them, and some of them you can apply kind of on your own. But this is just to show you how important it is for you to be able to understand how the hardware works so that you can write code in a way that interacts well with the hardware. Okay, any questions? All is clear? Okay. All right, well, you can read more about what we covered today in sections 5.10 and 5.14 of the textbook. That's all for today, and I will see you next time. Bye, everyone.